Good morning, everyone. Welcome to this special Pixel Club lecture. We're delighted to have Bahjat with us. My name is Elad. I'm the supervisor of Bahjat. Bahjat is finishing his PhD, one of the fastest PhDs in the Technion ever, I think. And one of the most productive ones, I have to say, on top of that. Amazing work on diffusion models. And we will be learning a lot about it in the coming hour or so. Bahjat, the stage is yours.
Thank you, Mickey. So do you have a picture? Yeah. No, I said. Okay, so thank you, Mickey. So my name is Bahjat, and I'll be presenting my PhD work on diffusion models for image restoration. So as we said, let's talk about diffusion models, which wow, thanks.
ואנחנו לא עושים על שום סטים טאבלים, רק על הרבה.
Thank you. So today's talk is about diffusion models, which up until a year and a half ago, every time I gave a lecture on diffusion models, I had to spend 15 minutes minimum explaining what they are and why they're useful. Here in this forum, we will still talk about what they are, but I think by now they're pretty commonly known. Yeah, so that's great. And specifically in my work, we use them for image restoration, so restoring images from degraded versions, also known as solving linear inverse problems, including very interesting ones such as resolution, painting, and ignoring. This was published in a series of papers. At first, working with Gregory Waxman, Alicia, and then collaborating with Xiaoming Song and Stefan Ramon from Stanford. Work has been published in Europe, and workshops at ICV and Europe as well. Over the course of my PhD, I was involved in 12 publications overall. 10 have already been accepted, 2 of them are still under review. And today we'll be focusing on these 4 red ones. Everybody do that themselves. All right, so let's start. We'll be talking about we'll start with the motivation, why we're doing this work, inverse problems, the problem we're going to try to solve. It's not a problem.
I think you need to press.
Yeah, awesome. So, all right. So, image restoration, or more formally, linear inverse problems. We're going to adopt the matrix vector notation. So let's assume that there exists a pristine signal x, which is just a vector that has underwent the degradation process. The degradation process that we're interested in is depicted by a linear matrix H, which is usually a wide matrix. So that means that just the operation Hx itself already incurs the loss of information because it projects us into a smaller dimension. And after this linear projection, we also, on top of it, assume that there is an additive wide Gaussian noise that is added. And this Hx plus z being the noise, gives us y, or noisy observation. So by only observing y, we're going to try and recover x. So if you recall from linear algebra, you can probably recover this using the pseudo inverse or something. It's not going to be good enough because H usually incurs a great loss of dimensionality, where you have too many degrees of freedom. Just the trivial solution is not going to give us a viable signal, a real image that we can look at. So that's where deep learning comes in. With solving problems like super resolution, where we're trying to enlarge an image, in painting, where we're trying to fill in missing pixels, or deep learning, where we're trying to unblur an image. We always need deep learning to fill in these blanks and learn what images should look like. And that's not even mentioning the problem with noise in the how it acts under a simplistic approach. So given one, we're trying to recover X. Of course, we are not the first to tackle this problem. So let's discuss a few of the previous approaches. And we're not going to discuss specific approaches, but we're going to divide them into two main categories. So first of all, anybody who took machine learning 101 would say, all right, just grab a huge data set of images, X. Given an X, you can easily generate the graded version Y, just do the H X plus Z. Then give Y to a model, some sort of neural network that is going to try to recover X, put mean squared error loss on it or something, train it to recover X. They would be right. That's a nice solution, right? It's going to work. It's going to give good performance. It's going to work. The inference time it's going to have good speed. It's just to apply the neural network. So that's not too bad, right? The problem is when you're trying to solve different kinds of problems. So if you train such a model for 2 times super resolution, how's it going to work for 4 times super resolution? How's it going to work with more noise, less noise? How's it going to work at all for in painting? It's just a different problem that the model was not trained for. So it's going to have poor generalization to other tasks. And it might suffer from the regression to the mean problem, which we're going to touch on in a minute, which is going to lead to poor perceptual quality in the results. What does that mean? That means that even if the result achieves good mean squared error or PSNR, it might not look like a good image, and we'll see an example of that in a minute. And the other category, which you might have guessed it's the one that our work falls into, is the unsupervised line of work. So we use pre-trained models to solve any linear inverse problem. So what we're going to do, we're going to take our deep learning element or neural network. It's going to model prior of images. It's going to learn what an image looks like. And then at inference time, when we're trying to solve the problem, we're going to incorporate our knowledge of the likelihood. That means the likelihood of the degraded measure given what we think the image is. Given the prior and the likelihood, using the base rule, we can obtain the posterior distribution. There have been many works in this category, including some of Mickey's group's previous work on regularization by de-noising. And given the posterior, you can give the most likely image, the map solution, can give its conditional mean, or you can sample from it. So please remember prior distribution, the distribution of images without looking at any specific problem or measurement. The likelihood is the likelihood of the measurement given what we think the image is. And the posterior is the distribution of images that are likely under our given measurement. So this type of work generalizes well for any task, can handle any linear inverse problem well, but it might come at the cost of slightly worse speed or slightly worse performance in terms of PSNR, in terms of distortion index. All right. So I promised to talk about the regression to the mean problem. So this is a figure from my second paper, SNPs, which we're going to take a little out of context. So what we have here, we have our original image, which we pass it through a compressed sensing pipeline. We project it into a random space, and then we randomly draw a certain percentage of the data. This is the percentage of the data kept. And the more we reduce the amount of data we keep, the harder the restoration problem becomes because we have less data to deal with. This is what you see in the first column, graded. And the second column, the sample, is what our algorithm returns. Here, our algorithm tries to sample from the posterior distribution we just mentioned, the distribution of images given this measure. And then there's the mean column, describes what a supervised algorithm would give. It's some sort of optimum over the mean square error ratio. So the mean will always have a better mean square error and a better PSNR than our solution. Now, when we keep only 25% of data, it's not that hard of a problem because compressed sensing works so well. Both algorithms can recover the image pretty nicely. And once we start reducing the amount of data we keep, the problem becomes harder. Because the problem becomes harder, if you look at the mean solution, even though it has better mean squared error, which is not shown in the figure, but it does, it looks less and less like an actual face. It has these artifacts, the amount of artifacts. Whereas our sample, although it looks less and less like the original image, it still looks like a valid face. Now, the thing is, because the problem becomes harder, it becomes more uncertain. And once we can sample from the posterior distribution, we can also look at the standard deviation of samples, and we can measure the uncertainty in the problem. So that's another good thing that is sampling from the posterior approach brings. You just sample our algorithm is stochastic, so we can sample many samples from this measurement and look at their standard deviation. That's what we did in the final problem. So that's what I meant by the perceptual quality. And that's not a concept that we invented. It's something discovered by Elad and Michaeli in 2017, their perception distortion training. Even though the mean solution gives us a better MSE, a better distortion metric, it looks worse perceptually. There's an inherent trade-off between these two concepts. Check out the paper for more details by Elad and Michaeli. It's a really interesting one. All right. So what we're going to do, the model that's going to serve as our prior images, what images look like, is going to be a diffusion model. So let's talk a little bit about them. As you all know, they're state-of-the-art generative models. These are images that were generated by Diffusion Model in 2021. Really, really good generative models. Let's see how they work. So first of all, if you look at here, we're going to define two processes. Given an image x0, we're first going to define a forward process. We're going to define x1, x2, x3 until xt. These are going to be our degraded versions of x0. And this is a definition that we're going to define using regular math. There's no deep learning involved here. And then there's the reverse process, which is going to try to reverse the degradation. It's going to try to go from xt to x0. This one is learned. We're going to use it to sample images, to generate images. How exactly are we going to define this forward process? So what diffusion models, or by the full name, denoising diffusion probabilistic models, DDPMs, do is that they define each xt as just an xt minus one, the previous one, with an added Gaussian noise. This is a Markovian model, because each node depends only on its previous one. And it's just, I'm not going to define areas here, it's just adding Gaussian noise. X1 is noisier version of X0, X2 is noisier version of X1, so on. And this definition, just by defining it like this, has two very good properties. First of all, even just by talking, adding some noise and adding some more noise is going to translate to adding a lot of noise at once. That's what this first property means. Take xt given just the x0, the image, it's still going to be Gaussian. So any xt is the same as x0 with some Gaussian noise with a certain level that relates to t. And so you can jump from x0 to x3 by just adding a lot of noise instead of just little noise. And the other good property is that once you add more and more and more noise, once you add too much noise, the distribution is just not going to resemble x0 at all. So the final xt, the capital T, is just going to be Gaussian. And that's what you see here on the far right. It's just a Gaussian image. And what that helps us do is that once we're trying to sample an image, in order to get our initialization, initial x capital T, you can just sample from this Gaussian without having any image before. All right. So again, we have the forward process, the one that adds noise, and the reverse process, which is going to try to transform noise into images. So I mentioned that the reverse process has to be learned. What are we trying to learn here? So diffusion models are generative models. They're trying to generate images. Our basic goal here is to have x0 resemble good images. Our method towards that, of course, as in any deep learning model, we're going to use a data set of a lot of images. So we're going to try to model. So what we're going to try to do, we're going to try to have the reverse process generate the training set images with a high likelihood. We're going to try to increase the likelihood of training set images. There's a lot of math that I'm going to skip over here, but what that basically is going to translate into is a KL divergence between both the forward process, the fixed Gaussian that we define, and the reverse one, which we're going to model to be Gaussian with a learned element. We're going to try to have both the distribution that is incurred by the forward process and the distribution incurred by the learned reverse process to look similar using the KL divergence. And once you simplify that, because both are modeled to be Gaussian, this is all just going to simplify into this loss, which is, all right, so you have your model, you have your X0, your training sample. Take your training sample, add some noise into it, turn it into XT, and then try to predict X0 from XT. Have the model try to predict what X0 should look like. So given your training sample, you add some noise, you get XT, and your model is going to try to predict X0 from XT. It's basically a denoiser. We know these. We've been working with these for more than 10 years now in the context of deep learning, and even more in a more wide context. So you're just training a denoiser, and this is going to be your engine to generate images. That's the core idea of diffusion model. All right, so you train that. Once you train, we ended up with a denoiser training. How do we turn that into a generative model that can generate images? So as we said before, we're just going to sample Gaussian noise in the beginning. We're going to give it to the denoiser, which, by the way, the denoiser knows the current place level, which is the T time step. So given this huge Gaussian noise, which is pure noise, we're going to ask the denoiser to try to predict the image given this noise. Of course, it's not going to make a great prediction in the beginning, so we're going to add some noise back. And then we're going to gradually iterate over this process. Every time we take our current image, we ask the denoiser to predict what the clean one should look like, then we're going to add some noise back, so on and so forth, until we arrive at the sample. So here, this is the denoiser that was trained on bedroom images. And after the preset number of steps, we get a sample that is a generated bedroom image. That's how sampling looks like. Another interesting way to look at it is to consider each update rule here, this predict and add noise back, as this update rule. So there's a theorem that shows that a denoiser can also be looked at as a score function. Score function is the gradient of the log probability of the image. So if we take our current image xt and we move in the direction of the score function, this is what applying the denoiser will give us. Moving into the direction of this gradient will increase the log probability, right? Just at this one, this is the gradient descent algorithm, trying to increase the probability of our current image. And we're going to add some noise perturbation in order not to get stuck in a local maximum. So this is called the Langevin dynamics algorithm, and it's an algorithm that is going to sample from the prior of images. It's going to generate an image that looks like the distribution of the training samples. Under both these interpretations, by the way, same algorithm, just different ways to look at it. It does not change anything about the actual mechanics of the algorithm, just different ways to interpret it. Under both these interpretations, the underlying model is still a trained denoiser. The algorithm is still the same algorithm, and we're still going to generate images. Just two ways to look at it, and we've touched on both interpretations in our line of work. Yeah, so this is the time for questions. Yeah,
More. This one you don't have control over what to be the image, right?
right. So this is just a generative model.
Random from the
You're going to try to generate an image that looks like the distribution of your training set. For more control, the text-to-image that you may have heard of, it's a small change to this algorithm, but we're not going to talk about that here. Any other questions before we dive into the work? Unmute the Zoom.
No, they can unmute or something.
Oh, I am unmuted.
No, if somebody wants to ask a question.
Okay.
But they're like, if someone wants a question or unmute themselves, or they'll post in the chat.
Yeah, a chat I'm not going to look at, but if anybody on Zoom wants to ask questions, please feel free to do so. Okay. All right. So these were diffusion models. These were diffusion models. Now we're going to use them to restore images. is where my work begins, basically. So we call that this is the diffusion model formulation. You have your forward process and your reverse process. And now we're gonna present the noise and diffusion restoration models. Another formulation that's gonna try to, instead of generate images, restore images, solve inverse problems. So this is our formulation. Looks very much like diffusion models, just that we added conditioning over the input observation all the time. So in the forward and the reverse process, each update here is dependent on y as well. We always condition on y, which are really y is just hx plus z. Its relation to x0 is very well defined with some noise. So do notice that even without talking about the solution to it, just the formulation here is dependent on the specific inverse problem. Formulation depends on the definition of h, on the noise level z. So the problem here is that I mentioned that supervised and unsupervised want to use the same model to solve all these different problems. How can we do that? We can use the same model, same diffusion model to solve all inverse problems when our formulation has to depend on y and on h. And if we're not going to do that, what's the alternative? So let's start with the alternative. How would you solve this diffusion restoration model? How would you optimize it? So a very, very straightforward answer would be, okay, you want to condition y, condition on y. Add y as an input to your denoising diffusion model. Have your diffusion model depend on y. Just train the diffusion model in the same way. You have your pristine image x, right, x0. Add some noise, then degrade it using your hx plus z. Add that as input. And then the diffusion model will implicitly learn to denoise, to denoise and restore the image from its degraded version, right? Right. That's a very valid idea. It was developed in parallel to our work. See works like Song and Saharia and Ackler and Seagraph. See the years very adjacent to our work. But and it achieves very, very good results. But the problem with this approach is that you're still going to need to train a separate model for each task that you're looking to solve. If you're trying to train a model for super resolution, you can. It's just not going to work for inpainting, as you trained it with inputs that are from super resolution. So this is where we come in, and we're going to try to use the same model for all inverse problems. In order to break down how we did that, we're going to actually go similarly to the different papers that we published. We're going to start with the simplest case, when our inverse problem is just denoising. So basically what this means is that h here does not exist. H is just the identity matrix. So our noisy observation is just our image x plus some Gaussian noise z with known variance. So, all right, let's look at diffusion models again. When you're trying to generate, which we call unconditional sampling, or trying to sample an image without any conditioning, you start from the beginning and you initialize with Gaussian noise and go through the reverse process. In our case here, we already have a noisy observation, we already have a noise image. First like these, right? The intermediate steps of diffusion models, as we have defined them, are just Gaussian noise contaminated images. So what we can find one that has the same noise level as our y, just initialize with y and continue from there. That's half true. I'm going to say the other half again, but we're just going to start from there. Do not, just by saying that, I have jumped over a few definitions that are important to notice. Once our noise observation comes into this definition, you notice that the noises in x1 and all the smaller x's, the ones with lower noise level than y, are now included in the noise level that I got in the beginning in y. So the noise in y is going to include these smaller noises from all the forward process. So I'm assuming that I started with the clean image and I added small steps of noise, small layers of noise to reach y. That's how we define our forward process. And we're going to take that into account when defining our reverse process, the denoising algorithm. So it's not just going to follow the regular diffusion update rule, which usually went like this. You start with our current image, xt, pass it through our denoising diffusion model, got the current prediction, time t. And then we add some noise back, some of the noise that existed in XT and some additional random noise. That's how diffusion model update rules work. You have your linear combination with different scalars. I'm not going to go into it, but you just denoise your image and added some noise back, some from your original noise and some additional new noise. What we're going to do, we always want to condition on our input y. Want to still sample an image that y will be likely given. That's why we add y into the mix. And that's our update rule. Just add y into the mix. And remember the two different interpretations, the score function interpretation. So before, in diffusion models, we just followed the regular unconditional score function, the gradient log probability, to increase the probability of the image. Right now, we are actually interested in the conditional score function. We want to increase the probability of our image given the noisy observation. This is the posterior distribution as opposed to the prior distribution. And using the Bayes rule, if we decompose this P of x given 1, it's going to go into P of x plus the likelihood term. Or because of the formulation of the forward process, it's going to include both y and the current xt, here x tilde. So
Will I be correct in saying that if you want to do super resolution in this scheme, you add noise only in the high frequencies?
not exactly. We're going to touch upon the general case in a few slides. But let's just focus on the denoising for now, because for denoising it's easy, right? Because both y and x are of the same dimensions. They both have similar noises, just one is more noisy than the other. So we can always look at the noise in the smaller x's as part of the noise in y. That's why this equation works. So instead of sampling from the prior distribution, generating the image, we're going to sample from the posterior distribution given our noisy observation y. Update rule is going to look like this, or under this interpretation, it's going to look like this. We're just following the conditional score function instead of the unconditional. So that would be noising. Yeah.
This is like restricted to wide Gaussian noise.
Yeah.
Like, did you try multiplicative or so?
We didn't.
Not like a group. You have sort of a group part of it you add.
Right.
A lot of times it was like a fixed step.
So we focused on wide Gaussian noise. We actually can deal with non-wide Gaussian noise as well. For different multiplicative noise and stuff like that, you're going to need heavier definitions to deal with that. Maybe even a change of the diffusion model, because diffusion models are inherently Gaussian. That's what makes it easier to deal with Gaussian noise. But yeah, for more complex noise, you need other formulations.
Extensions were made by several authors, including Gaussian.
Yeah. All right. So now let's consider a slightly harder problem. We consider just denoising. Let's consider denoising with missing pixels or in painting. So here, our H is going to be a diagonal matrix with ones and zeros on its main diagonal. What that means is that wherever the value is 1, we have our pixel with some added noise on top of it. Wherever it's 0, you have no information about this pixel. So look at this slide. This is an example of an input that we can get in this problem. Some of the pixels are missing. The non-missing, the observed pixels are noisy. We're going to try to simultaneously denoise and impede. How are we going to do that? We'll split into cases where we have observed pixels and unobserved ones. In the observed ones, we look very, very similar to the denoising we just saw, right? They're just pixels with noise. We can say that this one is Y or this one with the matching noise level, and just start from here and go on. But because we're trying to solve this on a global level for the entire image, we're going to have to start from the completely random noise. And we're going to split even here above, we're going to split it into 2 further cases. Before the noise level of Y, and after the noise level of Y. Before the noise level of Y, we actually don't have much to do, trying to converge to Y at this step anyway, right? Just trying to match the noise levels in all of the steps. We're going to formulate it that way. Then after the noise level of Y, it's just almost exactly the same as the denoising case. Just going to try to remove the noise from Y. So all of that can be described using the same scheme we just saw for denoising. you have your XT, you denoise it, you add some noise back, and you incorporate Y as well. Only this time, we only have to consider the observed pixels. We're going to ignore the bottom part. And then for the unobserved pixels, the ones we have no idea about, we're just going to do the same thing diffusion models do. We're going to try to generate these pixels. So we pass through a diffusion model, add some noise back with some additional noise, and that's it. Only this time we're just going to look at the unobserved pixels. You might say, okay, now you have these two cases, you do two pixels differently. How do you make sure that the image is coherent? How do you make sure that it's not just a completely different image from the one above? And this is where the iterative diffusion process comes in. Correct. Both the update rules are not very dependent, except for, do notice that this output is still dependent on all the pixels in the input XT. Same goes for the one before. Because of the iterative scheme, the pixels are going to affect each other every step. And the diffusion has a lot of steps, so it's going to work really nicely. So, all right, we solved denoising. So, in painting with noise pixels.
Okay, when you say do the reference process, why won't you start from the pixel that you know?
All right.
Why won't you start from the values and not from noise?
So that's a good question. We've actually tried that. If you start just with Y, right? You have your noise pixels that you know, and you have your unobserved pixels. What would you put in the bottom part?
The bottom part I put noise. And in every iteration, I'll try to denoise it. But I can try to denoise only the lower pixels.
So do notice that the lower pixels are, if you're just going to input noise, they're going to have a very high noise level. And the upper pixels.
In the iterations, I'll denoise it.
Yeah, but your denoiser is only used to deal with wide Gaussian noise. Now you're giving it different noises in different pixels. It's not going to deal with that very well unless you train it that way. And in order to train it that way, you have to train for every possible in-painting mask. That's what we're trying to avoid.
Okay.
We're trying to have the same noise level across all pixels. That's why we have to do this first few steps where we march towards Y, but keep the same noise level in all the pixels.
Okay.
All right. So now that we've solved denoising and in-painting, let's move towards the general case where we're trying to deal with any inverse problem, any degradation H. And now we're going to recall something from Mickey's course in bachelor's degree. Any matrix in the world, we can decompose using the SVD, the singular value decomposition. So any matrix, H, whatever it looks like, we always decompose it to U sigma V transpose, where U and V are orthonormal matrices, square matrices, and sigma is a rectangular diagonal matrix with the singular values in its diagonal. So that's the decomposition of H. And here's this statement. H is diagonal with respect to its spectral space. Spectral space just means the SVD space. What this sentence means is that if you transform your X's, your intermediate images as well as clean images by V transpose, and you transform your observations Y by U transpose, the relationship between the observations and the images is going to be this sigma, this diagonal. I mean by diagonal is that every pixel or entry in both the observation and the image only relates to a single entry in the other part. So every entry in Y only depends on a single entry in X. This allows us to formulate math much easier. Don't have to formulate each pixel in the observation as a function of all the pixels in the image. We're going to see some math on that, but that's the basic idea. Just transform your X's by V transpose, transform your Y's by U transpose. Okay, you're going to get this diagonal relationship, and depending on the singular value can be 0, which means this pixel is missing, similar to the in-painting algorithm, right? Missing pixel. Wherever it's not 0, it exists, only with some certain noise, you're going to denoise it, similar to the denoising case. So what we're going to do for any inverse problem, we're just going to transform our images and our observations by U and V. We're just going to run the same denoising and in-painting algorithm we've seen before, only in the spectral space. That means after transformation by U and V. And we provide a theorem in the paper that for any general matrix H, called that our formulation depends on H. So we do that likelihood objective, we do the KL divergence, we try to optimize the sampling from the posterior. If in diffusion models, they optimize for sampling from the prior, here we're optimizing for sampling from the posterior, or all possible inputs. To optimize this KL divergence, once we simplify OE, we arrive at the same optimal solution as DDPM under some conditions. What it basically means that we don't have to train anything. We don't have to train a model per problem. The optimal solution for any H under some conditions is going to be the same as training the diffusion model. This means that we can take the pre-trained diffusion model, the same one that the original DDPM authors trained, or the ones that OpenAI trained, and we took those. We did not have to train anything. Just wrote 4 papers on machine learning without doing any machine learning. We just took the model and changed the sampling algorithm to accommodate inverse problem solving. That was it. From this manner, what I see is T, including X0, the actual element, we transformed it by V transpose, added a bar to make sure we differentiate between them. Same goes for Y, we transformed it by U transpose, then we divide it by the singular values, which is going to change the noise a bit, but just the scalar, this is not a problem. And then there's this monstrosity, which is going to be overwhelming at first, but listen, let's look at what's happening here. This is the update rule defined for the forward process. Do notice that it's split into 3 cases. So when the singular value is 0, that's the same as the missing pixel in the observation. So if you look really closely, there's no Y here, because we don't have any information about this specific entry in Y. And the other 2 cases compare the noise level in the current XT with the noise level in our observation Y. So whether we're before Y or after Y. If we're before Y, we're going to try to converge towards it. If we're after Y, we're going to try to denoise it. And all of this is Gaussian linear combination of the X, the Y, the XT in some senses, in some cases, and an additional noise. I'm not going to go into the details here of the exact scalars and why we chose them that way. But that's the basic idea. That's the forward process. Then we model the reverse process, the learned one, as the same thing, only without depending on X0, the image, and replacing X0 with what the model thinks X0 is this point. When you try to minimize the KL divergence between the two, it's gonna boil down to MSE loss, which is have the model try to predict X0. This is the theorem, which just in broad terms just says that the optimal solution for the posterior sampling problem under this model is going to be the same as the optimal solution for DDPM. This motivates us to use the same model for all problems. Right? So for more questions specifically about the math, let's keep them for later. But if this is a broad question, then
yeah, just in a sentence, like, can you say something about the conditions? Broadly, what are the limitations?
Under some conditions, like when there. So some conditions, I basically mean the specific parameterization here. So we do have a hyperparameter here. So for a specific choice of this hyperparameter, the optimum is actually exactly the same. When you choose the hyperparameter a little differently, optimum is not exactly the same, but it's close, as long as you don't change it too extremely. So this approximation, you can say once you change the value of the hyperparameter, it's just similar to any approximation for any deep learning proof, right? Or deep learning proofs depend on your expectation being aligned with everything is IID. So it's not too much of a condition. We don't have any conditions over H. We don't have any conditions over the noise level. So this is still general to all inverse problem testing. All right. Another point here is that you may have heard that diffusion models are notoriously slow. They take thousands of iterations, talking about an iterative process. In DDRM, we actually depended on our collaborators' work, Chevy Song from NVIDIA, now NVIDIA, before that Stanford, on the DDIM, noise diffusion implicit models, which you may have heard of in the context of other diffusion models. It's an acceleration scheme that basically it just changes the update rule of diffusion models to turn them down from 1,000 steps into 20 steps without retraining the model at all. So we took some ideas from DDIM as well, incorporated them into our DDRM, the restoration models. And our formulation works really well, just 20 steps, doesn't have to take 1,000 steps. And that's a pretty good acceleration. And another thing, if anybody here has worked with SVD before on a computer, you know that it's very, very memory hungry. In order to do the SVD of the general matrix, you need a quadratic complexity in memory. That's still true here, but for most interesting problems, the matrices H, the relation matrices, follow specific forms that can be very easily simulated for the SVD without having to incur a quadratic memory complexity. So for denoise and super resolution blurring polarization, we just we wrote algorithms that can simulate the SVD with a very, very good accuracy without incurring a quadratic memory complexity. We also did that for press sensing, both the Fourier and the Walsh-Hadamard, but we didn't talk about that. So most interesting problems, the matrices can be decomposed into their SVD elements without having to incur a huge memory complexity nor a huge time complexity with the acceleration. So DDRM works really efficient. All right. To sum up for now, DDRM, we use a pre-trained diffusion model to solve any linear inverse problem task. Here's the examples below for super resolution in painting of large chunks of text and learn. Our algorithm, when we compare it to previous state-of-the-art and supervised methods, it has better speed and performance. And when I say performance, I mean both in distortion and perception metrics. It can work with noiseless measurements or noisy ones with any level of noise. And it does not require any manual tuning for its hyperparameters. So this last part, what I mean by that is previous unsupervised techniques usually had some few hyperparameters, but they tune differently for super resolution or deblurring or in painting. In DDRM, we did not have that. We had a simple set of hyperparameters that we chose just arbitrarily in the beginning what worked. And this same set of hyperparameters worked across the board for all noise levels, for all inverse problems really, really well. So it really is unsupervised in that sense. Okay, we're going to get into the interesting part of the presentation, which is the results. Some images, less math. So, but just before that, if anybody has any questions on Zoom also, please go ahead. Yeah.
In these examples, there is the training. Is it like the same model, or is it like a face denoising and
so that's a good question. We're going to touch upon that in the result. Here, and in the first one, it's a face model. Here, it's a cat model. But the images are not from the training set, of course. This cat, if you look really closely, it's taken this Ullman. It's taken in Technion. So it's not from the training set. And the pepper image, I think you might be familiar with it. It's a really popular test image. It's actually with an ImageNet model. This image is not from ImageNet. So what we found out, and we're going to show some results on that just using the ImageNet model, it's a good enough prior for any general content image. So we don't have to be class specific.
Yeah. And is it stochastic? So basically, you can run this multiple times. First image on the left,
so yeah,
accelerated one.
It is stochastic. If you recall the compressed sensing figure from the beginning, we showed the standard deviation. We're going to show some results for colorization. So let's just dive into the results because most of the questions here I have some figures for. All right. So for an overview figure, we have these different problems: super resolution, deblurring, and painting colorization. All of these are with small noise. As you can see, we can construct the images really well. It's ImageNet, bedrooms, and cat images. We have face images. And for super resolution, we had all these different variants of super resolution. So 4 times, 8 times, 16 times in each axis, as well as with or without noise. This is the same input image. You see that as the problem gets harder and harder, of course, our solution is going to stray further away from the original image, because you have less information to work with. But the image still looks like a viable face, still looks it still looks of high perceptual quality. Look at the image, you see here, this is a plausible solution for this. We deliberately do not show the original image here because just look at the observation. This is a good reconstruction of it. So we work, as I said, with or without noise for all these different problems. In terms of numbers, so we measure PSNR as distortion metric from the original image that we do not see during inference time. KID, which is similar to FID, to measure perceptual quality regardless of the input observation. And the number of function evaluations, the number of neural function evaluations is the number of times we apply neural network. It's linearly related with the runtime. You can see that DRM runs in 20 steps, beats all other competitors in both distortion and perception metrics. And other competitors need hundreds or thousands of iterations. So it's a really good acceleration. And you asked about general content. So this is using the image model. And these are traditional test set images. We added some blur and some noise to them, and we can give very good reconstructions to them just using the imaging model. This, by the way, these results were before the era of stable diffusion and DALI. So we did not have these general purpose diffusion models, but for restoration, it worked because it's in some sense an easier problem. So the imaging prior is good enough for this. And same for super resolution or times with noise. They reconstruct the images really well. This is for denoising, and this is the noisy image, the original one. This is what the ERM gives, and this is what just applying the denoiser gives us as a result. Both are really good at cleaning noise, right? It's a very good denoising algorithm. This one is supervised. It's follows the supervised way. Just passes through the denoiser model once and gets the output. It's good output. You can clean the noise really well. Actually achieves a better MSE and a better PSNR than our solution. If you look really closely at the hair, for example, I'm not sure if it shows well on the projector, but the specific hairs look better in the DRM. Finer details of the face here, 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 and here. You have more realism in the DRM result, so higher perceptual quality. That's because DRM attempts to sample from the posterior distribution, which is distribution of real images given noisy one. And this one just tries to minimize some sort of loss. In this case, mean squared error. Optimization problems do not consider the realism in the image, whereas a sampling problem can try to sample from the distribution of plausible images given our observation. That's one very cool advantage of posterior sampling algorithms. It was also discussed in Blau and Michaeli's perception distortion trade-off work. There's results for in-painting, both for randomly mixing pixels and studying text. You've seen part of these results before. And here's one of my favorite results pertaining to the stochasticity of the algorithm. So look at the original images here and their grayscale versions. Just took the image, passed it through a grayscale operator. And if you look only at the grayscale image, you with your worldview, right? You're a human, you've seen a lot of bears and grass and greenery. You know that the background is going to be some shade of green. You know that the bear is either brown, maybe black, and teapot. Maybe can infer the color, but not exactly. So if you look only on the grayscale image, even with your world knowledge, there are multiple plausible solutions to this colorization problem. So the bear may be more brown, more black. The grass may be more green, less green. And the teapot may assume different colors as well as its backgrounds. And these are actual samples from DDRM. Given the same input here with just different random seeds, we can sample from the posterior distribution. We can sample different viable results given this input. In the first slides, we showed also the standard deviation of these results for different problems. So we can also measure the uncertainty. Didn't go into that too much in our work. We showed an initial uncertainty quantification that I think Mickey and the other authors have also had more work on that later. So yeah, posterior sampling using diffusion models has a lot of advantages. Yes.
You have power to interface between stuff like this, like walking the latent space.
That's an interesting question to interpolate like across different
Yeah,
colors
here
here.
pick and choose and try to get to purple one with the red of the.
These are two different problems, but I see your point.
The idea is that if you get many samples, they create some sort of a cluster
Yeah.
that you can actually do SVD upon. And then you can navigate in major directions and actually traverse over all possible solutions
Oh,
and see the kind of solutions you can get in a very immediate way.
So outlet in space and in spectral decomposition.
Yes.
Oh.
So
I
that's
mean, it's very inspiring to see the kind of solution by 3-4 parameters, you see everything.
Yeah.
that's one approach to traverse it. In our work, we didn't touch too much upon this. We just provided different samples. You can always sample more, but to specifically control which shade of green and all that it requires more work. SVD of the cluster may be one approach, but yeah, it's an interesting future direction, right? And the final paper of this 4 papers, we extended the DDRM formulation to cover JPEG artifact correction, which, as you may or may not know, is not a linear problem. JPEG includes the quantization element, which makes it nonlinear. With some hand waving, we managed to apply DDRM to the JPEG problem as well. So here you can see images degraded by JPEG compression. You may have seen this by sending an image over WhatsApp or social media too many times. See that the compression ruins the image. You get this blockiness and weird colors. So DDRM can now restore that as well, with results on par with the previous state of the art in both perception and distortion metrics. This for different quality factors. Let's see the blockiness in the dot. It's almost completely removed. It's in the faces. That's one more thing that we could solve with DDRM. This, by the way, was papered in Europe's workshop, which is a continuation of the original paper in the New York's conference. And that's it for DDRM, but you all mentioned great points such as traversing the different solutions, maybe certain qualifications. There has been a lot of I mentioned that I wasn't the first to work on inverse problems, and also not the last. So after all these papers were published, they have inspired a lot of subsequent work. I'm going to mention a few of them that I find really interesting. So this group from Korea actually improved our algorithm, or posterior sampling algorithm, solving the same problem by backpropagating through the diffusion model itself in order to encourage the intermixing of different pixels. They have had many subsequent works, really good papers. I think they already beat DRM in some metrics as well. There's another group of, from China that also improved the results, known as DDNM. There's another group from Tel Aviv University, friends that improved upon the results in some senses as well for some problems. And this is a group from Japan that worked with Stefano Ramon, who was our collaborator on DRM. It came up with Gibbs DRM, which is generalization. They generalized DRM in order to solve line linear inverse problems. So our work was unsupervised. There's this line. What I mean by line is that we assume that we do know the H degradation at inference time. In their case, they have a parametric model for H. They know it's a deblurring problem, don't know the blurring kernel, something like that. And they mix ideas from DDRF and the Gibbs sampler in order to solve line linear inverse problems. They have really great results as well. Some folks have also taken DDRM to different applications. So this group from Finland, they applied DDRM to solve audio inverse problems. It's really interesting, and I have no experience in that. It's interesting to see DDRM used in that way. Another group is DDRM for strong, I don't know, there is something from Stoffel. They also show the standard deviation of their results. It's really interesting to see used there. And it was also used for hyperspectral image restoration, another specific type of image restoration problems, not necessarily related to our formulation of linear inverse problems. And that's it. Thank you for coming. Thank you for listening.
Questions?
Questions? Yeah.
I have a question on Zoom. Can you hear me?
Yeah, let me just try to increase the. Okay, go ahead.
So I think I missed something. I'm not sure I understood. Why do you need the SVD decomposition? If at the end what you want to do is compute the gradient of the posterior, then all you need is to add to the prior denoiser. All you need to add is the gradient of the likelihood. No.
So that's a really interesting question. If you look, we actually discussed this in SNPs, our second paper. Basically, if you just add the likelihood to your prior term, you notice that the prior is over your noisy intermediate image, xt. And you don't have an exact likelihood relation. So you have your xt, which is a noisy version of the ideal x you're trying to arrive at. And you have your observation y, which is a general linear inverse problem with h inside of it. It's an observation. So what's the relation between the two? We're not sure, because this one adds noise to the original image. This one degrades it and then adds noise. So we use the singular value decomposition in order to have this diagonal connection between the y and the x, the xt, more specifically. Without the SVD decomposition, your likelihood is going to be over x0, and your prior is going to be over xt, and it's not the base rule to connect the two, just add them together. It's not going to work.
But you can compute the likelihood based on your current estimate of the clean x in each.
Yeah, so that's what the group from Korea did. They backpropagated through the diffusion model in order to turn xt into x0. It's a really interesting idea.
Okay,
It's just a different approach.
thanks.
Yeah.
Yeah, thanks for the talk, right? You mentioned 20 iterations to listen to the results.
Right.
Is there a notion of doing it gradually? Like I do 5 iterations, get some result, do 5 more. Can I formulate it that way? So we've got time.
It's a really great question. We had a follow-up paper on that I did not present here. Right next to you have Noam, the main author on that. Here. So you can ask him about it. He did a really great paper that solves this exact problem. You have a gradual solving. You have your current solution. If you want to refine it, you can go on and continue the algorithm. Yeah.
How much time does it take to process like the inference?
So I don't remember exactly, but 20 iterations, I think it was on a regular GPU, it was around 2 seconds maybe. 3 seconds, I'm not sure exactly, but it depends on your hardware. That's why we don't talk about seconds, but it's an order of magnitude faster than previous approaches. The newer approaches had better results, but I don't think I've seen anybody reduce the time needed yet.
There is the line of work of consistency models.
So consistency models is interesting, but they do generation. They haven't worked on inverse problems just yet.
There is a bunch of those problems in the appendix, but the full truth.
Yeah. Any other questions?
Thank you very much.
Thank you.